Hello everyone, my name is Niranjan Nehra. I am PhD student at IISER Mohali. I would like to thank organizers to give me opportunity to talk about my work on image of Lie polynomial of degree 2 evaluated on nilpotent Lie. This is recent work with Shushma Rani. The study of multilinear Lie polynomials for Lie algebra is similar to the study of image of word maps in group theory. And one of the important problem in word map is or conjecture, which is that every element of finite semi-simple group is a single commutator. And this conjecture have been proved recently in 2010. And similar to this problem of group theory, a problem was formulated for Lie algebra and proved by Brown in 1963. That is every element of split semi-simple Lie algebra is a Lie bracket of element of L over the finite field and also over the finite field of sufficient bigger cardinality. In other words, basically, image of split semi-simple Lie algebra under the Lie bracket map is vector space. In fact, there is another problem related to this, that is image of multilinear Lie polynomial over field K on GLN is a vector space. This problem is proved for particular cases in n is equal to 2 or some fixed degrees like 2, 3, or 4. But still, this conjecture is open in all of the in general cases. A variation of this Livaux-Kaplan conjecture have been formulated in 2050, and that conjecture is following. The image of multilinear Lie polynomial over field K on classical Lie algebra is vector space. This conjecture followed for multilinear polynomial of degree 2 from the Brown's result of 1963, and for the degree 3 and 4, for some classical Lie algebras, they also proved this conjecture in those cases. We tried the similar problem, but not on the classical Lie algebra, on the nilpotent Lie algebra, and the starting point is basically multilinear Lie polynomial of degree 2. Our results for nilpotent Lie algebra are parallel to the results on finite P groups. So let me define the multilinear Lie polynomial of degree 2. Multilinear Lie polynomial of degree 2 is nothing but Lie bracket of x and y, where x, y are in L and C is non-zero scalar in the field. Let me define some notation that is the WL. WL is equal to x, Lie bracket of x and y, where x and y in L. Now let me define L dash. Let's define L dash to be the span of WL. Now the problem is converted like that, like WL, whether the WL is equal to L dash. In other words, that WL is a vector space or no. That problem we are investigating for nilpotent Lie algebra. First dimension of L dash is equal to 1, then WL is always L dash. So let me define nilpotent Lie algebra. So a nilpotent Lie algebra is a Lie algebra whose lower central series terminate at some finite step, that is Ln is equal to 0. If n is the least such integer such that Ln is equal to 0 and Ln minus 1 is not equal to 0, then we call that L to be n step nilpotent. And abelian Lie algebra is one step, that is L dash is equal to 0, L1 is equal to 0. We proved the following, that is that if L is finite dimensional nilpotent Lie algebra over the field K of characteristic not equal to 2, such that dimension of L dash is less than 3, then WL is equal to L dash. That is, WL is a vector space. But in general, WL need not to be a vector space. So what is true basically that if L is nilpotent Lie algebra of the following type, that presentation we are given, that is generated by U1, U2, U3, U4, U5, U6. U1, U2 is equal to U3, U1, U3 is equal to U4, U1, U4 is equal to U6, U2, U3 is equal to U5. For this Lie algebra, U6 plus U5 is not a Lie bracket of any two elements. We can show, one can prove this thing using the equating the coefficient, taking a commutator of any two elements and then equating the coefficient. And hence, that L dash is not equal to WL for its general nilpotent Lie algebra. Now the question is, when can it be equal? So what are the conditions? So in general, we are not able to determine the condition, but for the dimension of L dash is equal to 4, we proved a result. For that, we need some notations, and which I'll define as that breadth of a, so L is, if L is an nilpotent Lie algebra over the field K, and X belongs to L, then breadth of L, that is rank of adjoint map from L to L given by Y goes to Lie bracket of X and Y. That we call it to be breadth, that is rank of adjoint map. Now the breadth of Lie algebra is the maximum of breadth of all the elements of L. And if Lie algebra is finite dimensional, this is will be a finite non-negative integer. And if breadth type is tuple consisting of all possible breadth of so okay, breadth type is nothing but a tuple which consists of all possible breadths of element of L and written in an increasing order. So for the abelian Lie algebra, the breadth is 0. In general also, breadth is always is less than equal to dimension of L dash, because that rank of adjoint map is always, image of adjoint map is always contained in L dash. So dimension will be always less than equal to L dash. So now I'll state my theorem. Our theorem. This is recent work in recent work. So L is, let L is a finite nilpotent Lie algebra over the finite field of odd characteristic. With dimension of L dash equal to 4, then WL is equal to L dash if and only if one of the following holds. L is 4-step nilpotent with dimension of L is equal to 6 and dimension of Z is equal to 2. L is 3-step nilpotent with dimension of L is equal to 7 and dimension of ZL is equal to 3. If L is 2-step nilpotent with dimension of L is equal to 8 with the following breadth type, that is 0, 1, 3 or 0, 1, 2, 3, or breadth type of 0, 2, 3, which does not process any resonating set U1, U2, U3, U4, such that U1, U2 Lie bracket is equal to 0, U3, U4 Lie bracket is equal to 0. And in fact, when WL is not equal to L dash, that is not a vector space. In that case also, every element of L dash is sum of two commutative, two elements of WL. In other cases, this problem is open. And these are some references. Thank you.